In this video, I'm going to introduce quantitative statistical analysis when we're looking for the differences in two variables. I'm going to start by going over some terms that we've not yet covered in previous videos. I'm then going to briefly revise the base decisions that we should be making at the start of any statistical analysis, and finally introduce some statistical tests if your dataset has two variables within it. When you have two variables, it's tempting to use the term bivariate data, but if you're going to use this, you need to be very clear on exactly what this means, because this does not suggest that we have two columns of data. It tells us that the data we have is associated with two variables. An example is collecting temperature at a very specific time of the day. And if we have two factors associated with our data, then we need to be clear on what they are. And we often have an independent, which is a factor which will change regardless of what's happening. So time of day is a very good example here, because the time of day will always change no matter what else happens. The other factor is referred to as the dependent factor, and this is the one which is expected to change when the independent variable changes. Now these are very specific to when you have bivariate data. We can have two independent factors that we might be looking at what's happened, and we'll talk about those as we work through the video. The final term I'd like you to be clear on is matched pairs, and this is when we're talking about repeated measurements. And a repeated measurement means that the measurement itself comes from the same source. So for example, we might measure someone's mass before and after an exercise program, and that means that that data came from the same person. This is in comparison to looking at two different exercise programs and two different groups of people, and we can look at the change in mass that's happened before and after the exercise program, but they're from different people, so that would not be matched pairs. The base decisions that hopefully you've watched in a previous video are maintaining the same based on the scales of measurement. Remember that we do need to be very clear on the difference between nominal and ordinal, but our higher order, our interval and ratio, realistically we can just consider as scale, and we can group those together. If we use a very broad stroke, then we can say that the lower order is non-parametric and the higher order might be parametric. And to ascertain whether or not we're going to do parametric or non-parametric analysis, then we need to test the data distribution. But I'd also like to pause at this point and just point out that if we have higher order data that meets all of the assumptions of parametric analysis, the data still can be analysed non-parametrically. And this can be beneficial if you have lots of data sets and most of them require a non-parametric analysis, and then you have one data set which is suitable for parametric analysis. You might opt to do non-parametric across the board just to have a consistent analysis when you're actually writing up. The latest decision tree I'm going to introduce, I'm going to work through in partial stages so we can consider it in a portion at a time. Then I'll present the full decision tree at the end of the video, so you can pause and then make your copies of that if you wish. The first example that I'd like to go over is a lower order, so we know we're going to be working non-parametrically, and if we have nominal data. And hopefully you remember from your scales of measurement that nominal data is purely labels. So this is a categorical type analysis. And for categorical analysis, we use something called the chi-squared test. And what we're looking at is, if we expect something to happen a certain amount of times, does the recorded measurement of this occur as often as we would think? So you may say, I would expect to see this many of whatever I'm looking for. So if I'm in a particular area, then I might look at how many people have a specific condition. And then I could go out and then I could count how many people have that, and then I can use my chi-squared to see if these match up. The next situation that we look at, we have to consider two different scenarios. If we have lower order ordinal data, or if we have higher order data but the distribution is not normal, in both of these instances we're presented with two options, either the mann-whitney U-test or the Wilcoxon signed rank test. And the difference between the two relies on whether the data collected is matched pairs or not. And if you remember back to the start of this video, we know that matched pairs means that the data is coming from the same source. So I'll give you a couple of examples. If we look at ordinal data first, then if I was going to work with the mann-whitney U-test, I might ask some classes of students what their perception about how hard a test is. So I would use a Likert scale here, saying, do you think this will be Very easy, easy, you've got no idea, it will be hard or very hard. And because these are set points and we can't have any partial point between them, this is an ordinal scale. If I had a Wilcoxon sign rank, then I would need to get information from those same students at more than one point in time. So I could perhaps give them a survey using a Likert scale at the very start of term, and then halfway through the term I could give them the same scale to see if their perception of how difficult the test at the end of the year would be now that they've had a few lessons. If I went on a higher order type approach, then I would need some data that is going to fit into that scale type measurement. And a classic example would be the percentages that are actually achieved in a test. So for the mann-whitney U test, which needs the data to be not matched pairs, I could perhaps have two different classes that are covering the same curriculum but are taught by different staff, and we could look at how the students perform to see if there was any difference in the actual grades that were awarded. If I'm looking at the Wilcoxon sign rank test, you would need two tests to see if there was a difference perhaps halfway through the term and at the end of the term. So the examples here, you can see that even though we're actually looking at student performance or students' perception about the performance, the main difference is the way in which that original data is gathered. And this is really important, and this is why we have to be very, very clear on our scales of measurement so that we can understand which statistical test to choose. The final pathway through the decision tree is based on us having higher order data that's normally distributed, and then we're still presented with the same question: is the data matched pairs or not? But we have two different tests as an outcome. The examples here would be exactly the same as what we'd seen before. We would just be looking at independent tests, would be perhaps test information that came from two different classes and we were looking at their grade performance, and the matched pairs dependent t-test would be data from the same students at key points throughout the term. I should point out that there are some additional assumptions that aren't covered by this decision tree, and these rely on factors like there being an adequate sample size and that the variances in the dataset are approximately equal. You are expected to complete some additional background reading about these statistical analyses, and that's where you can find out these additional information and supplement the notes you are taking from this video. This is the full decision tree, and you can see that each of the stages that I presented in this video are available here. So you can pause the video at this point if you'd like to copy this down in full for your own notes. The final thoughts I'd like to put out to you in this video are that the decision trees are my own design. There are many, many other statistical decision trees, so please do look around, see if there's any that you prefer that make more sense or that you're just more comfortable using. This is an abbreviated list of all the possible analyses which could be completed, so as you read through different statistical sources, whether this is online or in textbooks, you are very likely to encounter other tests. This is not an exclusive list, this is just the most common tests that are used, and I think it's important that you understand these ones. As you work through background reading, then you'll find out more about the assumptions for these tests and the alternatives and the potential benefits of those alternatives.